Well, so earlier we have discussed about the rotational motion, and now we are starting with the chapter of gravitation. In gravitation, we have to go through with the various events like what's basically gravity. Gravity is basically a force due to which bodies come towards the planet when they are thrown away from the planet. So this is a common property of all the planets, or the stars also have the same property. Stars have got more powerful gravity as compared to the planets, and gravity is basically the force, or gravity is basically the attitude of the planet to bring back the body to its surface. Another thing is when we speak gravity, then we have to go through the weight, that why exactly we feel the weight of the bodies. Like, for example, if we put something on our palm of the hand, we find that our hand will be attracted towards the earth. So weight is nothing, it is also a force due to which bodies are attracted towards the center of earth. The another thing, that is weight is recorded with the help of spring balance, and mass means the quantity of matter contained by the body, and that remains constant always at all the places. Mass never changes, and it is recorded with the help of beam balance. However, weight changes at different places. Even at certain height, the value of the gravity changes, and hence the weight also changes. So in gravitation, the basic aspect to discuss is the law of gravitation, then how the planets move around the sun, and how the gravity works between the planets or between the star and the planets. So one of the laws is the law of gravitation, and gravitation is basically a phenomena in which there will be attraction between the two bodies for a specific distance. So the law of gravitation states that force is directly proportional to the force of gravity is directly proportional to the product of masses, and force between the two bodies is inversely proportional to the square of distance between them. This was first explained by Sir Isaac Newton. And this was later on modified by making certain laws by Kepler, and he stated the different things. That is about the elliptical orbit, that is, planets move in elliptical orbit. Moreover, they sweep equal areas in equal intervals of time, and the square of the time period of the planet is directly proportional to r to the power 3. That is, r is the distance between the planet and the sun. So these all facts we have to go through with. So whatever I have just now explained, now this is what we will just see in some of the expressions. Like number one is we are dealing with the Kepler's law. So there are three laws made by Kepler, and in three laws we find that there are definite regularities, found important regularities in the motion of planets. These regularities are known as the Kepler's three laws of planetary motion. Now, in first law, it is mentioned that all planets move in an elliptical orbit around the sun. This is what mentioned in A part. That is, first law is the law of orbits. All planets move around the sun in elliptical orbits, having the sun at one focus of the orbit. One more thing to be added in this context, that is, when we say the law of orbits, it is the point to remember, if a planet is close to sun, we will find that the ellipticity of the orbit will be less. But as the distance of the planet from sun goes on increasing, the ellipticity will also go on increasing. So the orbit of Earth is more elliptical as compared to Venus or as compared to Mercury. But if we just proceed towards Jupiter or Saturn or Pluto, we will find that ellipticity will be very high. And at Pluto or Neptune, we will find that ellipse is just like both the curves will appear to be meeting, and it will become just a hyperfine straight line. So it means that distance from sun to the farthest planet, that will be very, very large, and ellipticity will be very large. Almost two curves appear to be coinciding, however, they are not coinciding. Now, in the second law, we are finding that this is called the laws of area. Now, in this one, a line joining any planet to sun sweeps out equal areas in equal intervals of times. That is, the areal speed of the planet remains constant. So, what exactly we mean by this? That is, the planet is moving in an elliptical orbit. So, when it moves, then from one point to another point, it will sweep equal areas in equal intervals of time. And moreover, the speed that will vary. For example, when the planet is close to sun, its speed goes on increasing, and when it is farther away from the sun, we will find its speed will be decreasing. So these facts are to be discussed. So according to second law, when the planet is nearest the sun, its speed is maximum, and when it is farthest from the sun, then its speed is minimum. So we can refer to the figure. In the figure, it is shown if a planet moves from A to B in a given time interval and from C to D in the same time interval, then areas AS, B, and CS, D will be equal. DA is a small area, that is area of the curved triangle SAB. So we can refer to the figure, that is SAB, and the angle between BS and SA is given as d theta. So we find that DA, that is the area of the curved triangle SAB, that is given as half AB into SA. Now, what is basically AB? AB is the area swept, or it is moving in circumference, multiplied by SA. Now, we are finding SA, that is equal to R. If the axis of sun is joined with A, the total angle will be theta, but the shaded region will be a small angle traced from A to B, and that will be d theta. So, dA can be given as the area of the curved triangle SAB, and it can also be written as half within the brackets r d theta multiplied by r, or this is equal to half r square d theta. This is called the law of areas. So when the planet is in the region O2 or S2A or S2B, we find the speed is gradually increasing. But however, the speed will be minimum when it is at the farthest distance. But when it comes to position C or position D, we find that the speed of the planet will be drastically more. So in this region, shaded region CDS, the speed is maximum, and in the shaded region ASB, we find that the speed will be less. And area can be estimated by function half of AB into SA, or half r d theta into r, or this is equal to half r square d theta. This instantaneous areal speed of the planet is dA over t, that is derivative of area with respect to time. So we compute the value of A, and the function will become half r square d theta over dt, where half r square we have written as it is, and derivative of angular displacement with respect to time, that is called angular velocity. So theta is the angular displacement and omega is the angular speed. So we have taken the derivative of theta with respect to time, and that becomes omega. We have marked it as equation number 1. Now, omega is the angular speed of the planet, and normally the representation of angular momentum is L. However, our assumption here is J. J be the angular momentum of the planet about the sun. M is the mass of the planet. So if these are the assumptions, then in that case, the angular momentum J or the basic representation L also is there, but however we have assumed it to be J. So angular momentum is given by function I omega, where I is mr square, m is the mass of the planet, and r is the distance of the planet from sun, and omega is the angular speed. Now this we have marked as equation number 2, and wherever uh, you see, we will write r square omega, and we'll take half and multiply by m, we can replace it by j. Now, same figure is applicable here. R is the distance of A from Sun, or as the planet is moving from A to B, we find gradually the speed will increase. When it comes to position C and towards D, the speed will become maximum. So now I is mr square. It is the instantaneous moment of inertia of the planet about the sun. Now from equation 1 and 2, which we have discussed earlier, we will find derivative of area with respect to time will be J over 2m, and we mark it as equation number 3. Well, as I have explained you earlier, J is supposed to be the angular momentum, and angular momentum is given as I omega. I can be replaced by mr square, and when we say angular momentum is I, that is angular momentum I is equal to I omega. I means mr square and omega means v over r. Now, the areal speed, now we have to go through the speed. So it is dA over dt of the planet, and that is constant. Areal speed. So areal speed is represented in terms of derivative, that is derivative of area with respect to time. So it is dA over dt of the planet is constant. That is, the areal speed is constant. So whatsoever the position of the planet, areal speed will be constant, and according to Kepler's second law, therefore, according to equation 3, the angular momentum J of the planet is also constant. Angular momentum of the planet is conserved. That is angular momentum. That is, second law is equivalent to the conservation of angular momentum. And now we come to the third law, that is square of the period. That is, we know that time period of planet is given as 2 pi r over v. For v, we will put the value of speed, and r is the distance of the planet from sun. If we compute the value of v, we will come to a relation in which we will come to know that t square will be proportional to r cube. So this is depicted here. Proof is given to us. So in the third law, that is called the law of periods, we find the square of the period of revolution, that is time of one complete revolution. So time is taken as distance over speed, and time is 2 pi r over v. So the time of one complete revolution of any planet around the sun is directly proportional to the cube of semi-major axis of its elliptical orbit. Semi-major axis. So next is now the proof of the statement that if A and B are the semi-major and semi-minor axis, it will be shown in the figure, then the area of the ellipse will be AB. Hence, if T is the period of revolution of the planet, then T is equal to area of ellipse over areal speed. And for that, we have given a mathematical formula, that is area of ellipse will be pi times AB, and areal speed will be J over 2m. And from this expression, if we take the square of the number, we will find the number will become t square on the left side, and on the right side we'll find it will become 4 pi square m square a square b square over j square. Again, I am repeating, j is angular momentum, and that's value is I omega. Now, if L is the semi-latest rectum of the elliptical orbit, now we are using coordinate geometry here for finding the latest rectum. So L is the semi-latest rectum of the elliptical orbit, and this semi-latest rectum is given by function B over A. So B and A is basically are in the semi-major axis and the semi-minor axis of the ellipse. So we are using the coordinate geometry of ellipse, and L will be calculated by formula b square over a. Now t square is known to us, or now compare t square with a cube, because pi, m, l, j, etc. are constant. So what we have found that t square is proportional to a cube. A or r is the same thing. R means the distance of the planet from sun. A is also the distance of the planet from the sun. The period of revolution of the closest planet, Mercury, is 88 days, while that of the farthest planet, Pluto, is nearly 248 years. That is what the period of revolution. Like for Earth, the period of revolution is nearly 365 days. That constitutes 1 year. So similarly, if we proceed to Mars, we will find the time period will be more. That is, planet is moving very fast. Well, Kepler's law is indicated, or this is a demonstration of the Kepler's law. Sun is at the fixed point, and the green portion is indicating a planet. This planet will move in the elliptical orbit. This is what known as the first law of Kepler. So this is moving in the elliptical orbit, and moreover, when it is close to sun, its speed increases, and it is away from the sun, its speed decreases. Now, in the second law, it is depicting the second law, that is, the planet is moving around the sun. It sweeps equal areas in equal intervals of time. So, whether the planet is moving from P to Q or M to N, we'll find that the surface area will remain same. And according to the third law, whenever planet is moving in the elliptical orbit, then the square of the time period will be proportional to the cube of the distance swept by the planet around the sun. And in the inverse square law of gravity, the force of gravity between the two bodies is inversely proportional to the square of distance between them. This was explained by Sir Isaac Newton, and also one more point was explained, and that is the force is directly proportional to the product of masses, and in addition, he explained that force is inversely proportional to the square of distance between the two bodies.